All right, so my name is Adriaan Duivenvoorden. I'm a postdoc at Princeton University. I'd like to thank the organizers for giving me the opportunity to talk. I will talk about data analysis challenges for ACT and SO, and because at Princeton I work on both these experiments, the Atacama Cosmology Telescope and the Simons Observatory. Right, so I will start with a short overview of these two experiments, and then I'll get into some of the challenges. Clearly, these will not be all the challenges we face, but I picked a few that I think are relevant to this conference and also the ones that I am most familiar with. So let's start with an overview of the Atacama Cosmology Telescope. You can see it here on the right side. It's inside this big ground screen, and it's situated in northern Chile in the Atacama Desert at an altitude of more than 5 kilometers. So it's very high up. Being in northern Chile gives you access to a lot of sky, and we sort of make use of that. So ACT now maps about 40% of the sky. And ACT is a pretty large telescope for CMB science. It's 6 meters, which gives you, if you compare it to, for example, Planck, a lot more sensitivity at high L. So here is a timeline of the ACT observations. So these started in 2008. And what you see here are sort of different iterations of ACT. You can think of them as different cameras that are placed in the telescope. So this started in 2008 with these 3 detector arrays that actually were not sensitive to polarization. Then later, in 2013, roughly, the next iteration called ACT-POL started, which comprises of these 3 detector arrays that observe at 90 and 150 gigahertz. And then that's transformed into what we call advanced ACT, where we added, or we replaced the 3 arrays with 3 new detector arrays, observing in, again, 90 and 150, but now also 220 gigahertz. And then most recently, we've swapped one of these arrays out for another array which observes at lower frequency at 30 and 40 gigahertz. And another thing that's important to note is that ACT used to observe fairly small patches of sky, but then gradually we started to observe more and more of the sky, and now we are observing this 40% patch of the sky. Okay, so now I'm going to talk a little bit about the recent data releases and the upcoming data releases. The first one I'm going to talk about is what we call ACT-DR4, data release 4, which includes this ACT-POL data from roughly 2013 to 2016 in these 2 frequencies. The main results are described in these 2 papers, focusing on the spectra and focusing on the maps. You can see on the right-hand side here some of the results showing the CMB spectrum that we get. The maps and the likelihood and all these products are all publicly available. So roughly at the same time, we also released ACT-DR5, which is slightly different. It's this data release comprised essentially of one map, which is a co-added map of all of our data up to 2018, together with 3 channels of Planck HFI. So the rationale of this is that even though some of this ACT data was relatively preliminary, ACT is really good at measuring these high L data, It's really designed to do that. And it's less good at measuring low L data mostly because of the atmosphere. So most of the time spent in our data reduction is spent on understanding the low L part of the data. And so with this data release, we sort of circumvent that by adding in Planck at low L. So this co-added data set is great for this sort of high L science, but it has some caveats. There are no splits, for example, no independent data splits. We have no simulations, and some of the data is a bit preliminary. But still, I think this tactic worked out for us. It's been a very valuable data set for example, cluster science. And again, this data set is available. You can also go to this link and see the map in your own browser, which is, I think, very nice to see. Here, I've taken a few examples for you to look at. So here you see a patch of sky observed by Planck, and then here you see if we add in ACT, so this is the co-add of ACT and Planck, and if I flip between them, you see the large scales are mostly given by Planck, but ACT adds in fine structure, and you can really suddenly see all these point sources pop up. And in this picture, you can also see two very obvious SZ clusters, which at 150 gigahertz end up in the map as these decrements in temperature. One other plot here showing over a fairly large part of our patch the E mode map. Again, this is Planck and ACT, but it shows you, even though this might look as noise on Zoom, but I can assure you these are all very or pretty high signal to noise modes that we're measuring all over the sky. You can see by eye. All right, so now going on to a data release that's in future. So that's ACT DR6. This analysis is still underway. This is comprises of a large part of this advanced ACT data set. So these three frequencies, 90, 150, and 220 gigahertz of these new detector arrays. And what we're specifically including is the data from season 17 to season 2021. And we have chosen to jointly map all of the seasons. So previously we would map separately different seasons. Now we've mapped all of it together, which gives us the nice property that we can make this 8-way split of the data, which is useful for noise estimation. Just for general interest here, that roughly the data volume comes down to about 200 terabytes, which is about 10 times that of DR4. And here on the right side, you can see some plots showing how good this data set will be. So on top, you'll see the case for temperature, and the bottom you see the case for polarization. And these plots, the way to read them is that on the x-axis, you see the area at which all of the data is at a certain sensitivity or better. One important caveat here is that this is the white noise noise level, and as we'll see, the ACT noise is not really that white, especially at low and intermediate L's. At high L, it's pretty close to white. And then what you see here is ACT DR4, ACT DR5, and DR6, and you see this massive improvements. We've got very good noise levels over a fairly large part of the sky. And in polarization, the improvement is even more impressive. Okay. Now, briefly mention Simon's Observatory. So this is a future experiment that's being built right now. It's right next to ACT. or will be right next to ACT in the same spot. It will observe in 6 frequency bands. We'll have a very large number of detectors, and it's being built as we speak. This year, the validation is planned. First observations are next year, and then there will be about 5 years of observations. Excitingly, this week, actually, I can show you. Well, let me first show you this. The SO will comprise of 2 types of telescopes. So one large aperture telescope, which you see here. I think of this as a newer and better version of ACT. It still is a 6-meter diameter telescope, and we're planning to also map about 40% of the sky with this one. But then additionally, we have these small aperture telescope, 3 of them, which are much smaller diameter, and because they're really not designed for the same science as the large aperture telescope, instead they're designed to go after the polarization over large angular scales, mostly looking at B-mode polarization. These will additionally have a fast spinning half-wave plate. Also, another difference is that these will not look at all of the available sky, but look at about 10% to sort of have a deeper observation than instead of having a wide observation. Okay, so what I was going to say is that this week we got some exciting news. Here on the left, you see a picture taken from a drone that we'll plan to use for calibration. On this picture, you can see ACT here, and you can see the bases for the 3 small aperture telescopes and the base for the large aperture telescope. And 2 days ago, on top of this concrete base, the base itself for the telescopes, for the small aperture telescopes, was being placed. So that's an important milestone for us. Okay, so now with those overviews of the experiments out of the way, I want to talk about some of the data analysis challenges. Well, I'm again skipping ahead. Here, one other thing is for people interested. These are the science goals of Science Reserve 3. I don't think we'll go over this too much. The one interesting takeaway I think from this is that many of these science goals don't just rely on the sort of traditional power spectra, so the T, E, E, and BB power spectra, but they instead rely on the lensing power spectrum or the kinetic or thermal Sunyaev-Zeldovich effect. So we're really getting to the regime where we're using these sort of secondary probes of the CMB as full-fledged science. All right. So now going on to the data challenges. First one I want to talk about is the atmosphere. So as we're on the ground, most of the noise we see is due to the atmosphere. And the plot here on the top right shows you sort of a typical power spectrum of the time order data. And you can see this very steep rise, this 1/f spectrum, which is mostly due to the atmosphere. You can see that at 150 gigahertz, the red line, the noise is stronger than at 90 gigahertz. That's due to the sort of spectral behavior of the atmosphere. So in our data analysis pipeline, we use what people call maximum likelihood map making. It's not, the details are not so important. What's important, we model the atmosphere as noise. It's considered noise. It's modeled as a 1/f type spectrum. It's very crucial actually to include correlations between the detectors and the noise model. So what that really, it's easy to understand. The atmosphere, if you think of it as consisting of sort of clouds or sort of hot blobs of different sizes. Um, Detectors on the focal plane see the same atmosphere at the same time. So at low frequencies, this 1/f spectrum is very correlated between detectors. At high L, it's less of an issue. So we do include those correlations in our noise model, but it's still a relatively simple noise model where we have this 1/f noise spectrum that's assumed to be stationary over 10-minute timescales with these correlations between the detectors. So one possible improvement that I think is very interesting is taking into account the wind direction. So if you see here on the bottom right is a plot of a similar or the same power spectrum in the time domain, but now showing the ratio of that power spectrum for left-going scans and right-going scans. And the different colors show you the difference between the relative velocity of the atmosphere compared to the detector between left and right scans. The takeaway of this plot is essentially that when you're scanning with the wind versus scanning against the wind, you can have quite drastically different noise properties. So I think one challenge, or let's put it, a fun project would be to incorporate our knowledge about the wind direction in the map maker. So make a map maker that understands that what the wind direction is and will weight left-going and right-going scans in different ways to improve our optimality. We're not doing this for ACT, but we're definitely looking into it for SO, as well as looking into quite advanced modeling of the atmosphere to create simulations, but I won't go into that now. Okay, the other challenge I want to talk about is what we call pickup. So pickup, sometimes referred to as ground pickup, but it's not entirely clear that every part of this signal comes from the ground. It's some roughly scan synchronous signal that contaminates our map. On the right here, you see an example. This is a cutout from one of our DR6 maps. This is Stokes I at 220 gigahertz, which shows the worst pickup. And it basically manifests as these horizontal stripes in the map that can be quite bright compared to the sky signal. They're also quite polarized. The good thing is they are really just horizontal stripes, and so they're sort of sparse in the Fourier domain, which allows us to filter them away. And we've been using different tactics to do this. So in the new data set in DR6, we are just leaving the signal in the map and then relying on a Fourier filter to filter these modes away in later stages of the analysis. Well, in DR4 and previous ACT releases, this pickup was we tried to model and subtract it during map making. But we stopped doing that because it didn't work as well as we would like, and it made our maps slightly biased, and it was difficult to quantify that bias. We think now with doing this filtering the map domain, it's at least easier to quantify the bias. And it is quite effective, this Fourier filter, but I would say it is quite painful in combination with all of the point sources that we have in the map. You are forced to either in-paint or source subtract the maps when applying the filter. So I think for going forward with SO, it would be wonderful to have a better way of modeling this pickup in the time domain during map making, or to have a more advanced map-based filtering approach. I think this is a big challenge for us. Then one other challenge, which is perhaps a bit vague, is what I call model errors. And let me try to give some context for this. So here on the right side, top right side, you see noise spectra for the DR4 data release for the different arrays and the cross correlation between the arrays. The point is that at low L, as I said, due to the atmosphere, there's a lot more noise than at high L. So there's a quite large dynamic range between low L and high L noise. And I think it's fair to say that this dynamic range will only increase with more sensitive data, because at low L, your detectors are not sampling, or the noise between the detectors is very correlated. While at high L, the noise between detectors is more or less uncorrelated, so you average the high L data down faster than at low L. So with this dynamic range only increasing, I think we have to start worrying more and more about these model errors. So what I mean by the model error, it's an error in the model, not in the way you characterize the noise, but in the way you characterize the signal. And so examples of this are assuming that the sky is pixelized, which is obviously not actually true, having errors in the pointing of the telescope, having errors in the gains, etc. And the most scary model errors are ones that happen on small scales where you have lots of signal to noise, but are influenced by large scales. One example is, think of a large gradient in the CMB that on small scales, due to the pixelization, gives small model errors. Because of the difference in signal to noise on large and small scales, MapMaker is very happy to sacrifice the large scale fit in order to make the small scale fit better. And so that sacrifice at large, at low L is incorrect. So you will introduce a bias from this. So a lot of our work now is trying to understand that we include all of the right model errors. The good thing is that this is generally less of a problem in polarization because the dynamic range and the noise power is much less a problem there. So I think this warrants a lot more thought for upcoming data sets. I think we're starting to see that this starts to matter more and more. Okay, then I'll go on to another challenge, just noise modeling. So in our analysis, we rely heavily on noise simulations. And they should be as accurate as possible, obviously. So one thought you might have, and I certainly had, that if we are able to model the noise in the time domain, as I said, with this 1/f spectra and the correlation between the detectors, it must be okay. It must be possible for us to generate accurate signals of our noise. Turns out for ACT, this is not quite true. That model doesn't work as well as you would like it to be. And very importantly, it's very expensive, right? Our map making is very expensive. So we really can't afford, or at least we're not doing it, to generate many time-ordered SIMs. This might change for SO, by the way, but for ACT, we're sort of stuck with trying to model our noise in the map domain. So we're using this very empirically based model where we use different data splits to find out what our noise is in the map domain and then try to model that. So I'll talk about that, what we're doing right now, and a bit about how what we could do in the future. I should note that one partial solution to this noise modeling problem is relying on what I call split-based estimators. So as with a split, I just mean a split of the data into two or more parts that have independent noise. I think we're all familiar with using a cross-correlation estimator for the power spectrum, which avoids the noise bias from the noise. But you can construct these for other things as well. And especially this one that I point out here, where you use 4 independent splits to construct a lensing estimator that is very insensitive to the noise modeling, turns out to be very useful for us. So I think going forward, these sort of estimators are really the way to go to sort of reduce the sensitivity to the noise modeling, which is hard. Okay, but now moving on to our noise properties in the map and the stuff we're trying to simulate. So ACT, as I said, is this very red noise power spectrum, but it's more complicated than that. The noise is correlated in a sort of stripy manner. That's due to the scan strategy mostly that we have. Here I show in the bottom right an estimate of our noise. So this is just basically two parts of the data difference. So the signal mostly cancels and we're left with noise. Plus, by the way, some residual galaxy and some residual pickup, but we'll ignore that for now. But what I then show is in 2 parts of the sky, I compute the 2-dimensional power spectrum. So if you're not familiar with these plots, in the middle of the plot is basically the monopole, and then go out, you go to higher wave numbers. For these plots, the symmetric part is subtracted, so we're left with the asymmetric part. And you see these very clear stripes in the Fourier space, which corresponds to these stripes in the noise that you can also see by eye, more or less. And the important thing is this structure varies over the map quite a lot. So that's a complication we have to deal with. Another complication we deal with is that the map depth, so the sensitivity essentially varies over the sky, but it also varies with angular scale. So that's shown in these 2 plots here, where what you see is an estimate of the inverse variance per pixel, but on different scales. So on the top, it's scales that are fairly large, and here on the bottom, fairly small scales. And you see the morphology is quite different. And really the morphology in the top panel is again determined mostly by the scanning pattern on the sky. While on the top, in the bottom, it's mostly determined by, let's say, the number of hits per pixel. So we need to be able to simulate this. The way we do this is to start from I'm going to be very, this is going to be very, well, I can't go into details, I don't have time, but we'll start off with the assumption that the power spectrum is a good starting point, but not great. And then we model the deviations from the power spectrum with a wavelet-based method. And these wavelets then capture the spatial deviations and also the directional deviations from the noise described by the power spectrum. I want to say most of this work, hard work, has been done by Seth Atkins at Princeton here, who's developed this method. You can look at it here. And now we'll show you some preliminary results. So here, I'm again showing you 2 of these noise maps of the data itself. Again, showing the 2 power spectrum in the 2 regions. Then the bottom plot here is now Stokes Q as well. And then here I'm going to show you the simulations. And you can see that we do capture quite a lot of the sort of complications of the noise. So if I flip back and forth, you can sort of compare it by eye. And because we're using these directional wavelets, we are capturing this sort of complicated directional noise that varies over the sky. All right. Now I am almost done. So these map-based sims give us a relatively cheap way to simulate our noise, which is exactly what we needed for ACT. We are still in the process of checking whether we're not running into problems with overfitting. This turns out to be quite a difficult thing to check. We're relying on 4-point statistics such as the variance of the power spectrum or the lensing estimates to do this will be described in this upcoming paper. For SO, I think this method is very promising, but it would be also very interesting to think about whether we can not use a purely empirical method like we're doing now, but really try to rely on some statistics that the map maker can provide us, such as sort of a hits map and a cross-linking map to help us build this model, because we do understand sort of where a lot of the structure and the noise comes from. So I think this will be a great project for us to work on. Okay, then I'll be very quick about this. My final challenge that I wrote down was a way to optimally filter the maps. So many of our estimators rely on, or at least ideally would rely on optimally filtering the data, which is a very expensive thing to do when you are when you're filtering by both, by the inverse of the sum of the signal and the noise. So for ACT and SO, we've been trying to extend the method that was developed for Commander to our needs. And I'll be happy to talk about this later on. I'll be very brief about it. I think the main thing we've added is this wavelet-based noise model that I just talked about in this method of doing this, which also will be described in the upcoming paper. But again, this is an expensive and hard operation, so we can still improve this for SO. Okay, and here is a summary. I've talked about the different data releases for ACT. The DR6 data release will be a multiple stage process. We'll start off with the lensing results, and then the power spectrum and the maps release will be later. Then I talked about some of the challenges I've listed here. And finally, the thing I've not talked about is that we also have this really great 30 and 40 gigahertz data that will come up and will be released later on in what we'll call DR7. I'm running out of time, so I'll leave it at that, and thank you.